China Information and Communication Technology Group. Its original name is the Fiber Hall Technology Group. My name is Zheng Hao. My title is real-time implementation of the 3-stage equalizer for burst mode digital QPS receivers of the coherent PAM. Here is the outline of main content about the abstract, background, and proposed architecture and real-time implementation, and the experiment setup and the result and the discussion. The final is our conclusion. In this paper, we implement a real-time 3-stage equalizer for burst mode digital coherent receiver in asynchronous PAM upstream and demonstrate a high performance multifunction parameter headers. We evaluate the performance of this architecture in the real-time experiment. In most commercial coherent communication systems used in the long-haul markets, the demoted signals are sampled by the recovered clock and processed by the DSP. They are didactic N-type butterfly FR perform the polarization demultiplexing and compress the intersample interference, include the dispersion and other filter effects. But in the upstream direction of optical access network, the OT must deal with the burst data frame from one resolve U, which requires the clock servo and the butterfly to converge as rapidly as possible, which constitutes a huge challenge to its feedback-based architectures. So the converge time will consume the thousands of samples to demarcate by packet. In our former work, to overcome the lighting-induced ultra-fast SOP rotation, we employed a 2-stage equalizer. The training-based feed-forward one-type butterfly MIMO. That's the second stage is used to compensate the SOP rotation. And the first stage is updated by the joint CMA to compensate the ISI effect. This architecture achieves the 20 megahertz ultra tracking speed, ultra fast tracking speed. This is the fastest reported in as we know. But when we use this in the upstream pulse, we still have left problems. Because the sample clock must be recovered and located to the different ONUs, which will consume thousands of samples. Although the adapted FR can compensate the sampling phase offset, but the converge times will need hundreds of sample period. The more serious problem is if the sampling phase slip very fast, maybe the adaptive filter can't track this fast slippings. So we proposed the 3-stage equalizer. The equation is like this. The first stage is feed-forward interpolators. It calculates the sampling phase offsets and compensate it by the interpolations. The second stage is to compensate the slowing, varying, intersample interference effects. We use the pre-calculated filter coefficient as the initial values and use its adapted filters. The second stage is feed-forward one-type butterfly MIMOs. In this paper, we use the FPGA-based platform to implement the 3-stage architectures. And especially, we designed a multi-function training headers, which achieve the Feynman centralization free of polarization rotations. This header is also used to cause frequency offset estimation and SOP estimation together. The sampling phase is calculated from the sliding sample blocks by the square and filter techniques, with the absolute value of delta t smaller than the 0.5. To avoid the repetition and omission inside one frames, we introduced the delta t used, which ensure to not exceed the boundary of the interpolators. Now we introduce our the Feynman centralization techniques. Afterwards, sampling phase offset and inter-sample interference has been compensated by the first stage. The result is the output result is like these equations. So we do the conjugate product to adjust the data like these equations. After the deductions, the final result will like this. We can say this because A and B is the element of the joint matrix. In this equation, the A and B disappeared. So this result is not affected by the polarization separations. And we can use the local correlation calculation to find the central frame headers. The local pattern can use the data from the X polarization or Y polarization. We can choose freely. This we call the local correlations. Because the local correlation we can find it's include modulation remove process. So the frequency offset can also obtained in this process. By the way, although the local correlation is accurate, but it's very complex in this implementation. It's different from continuous mode transmission because we must attempt each possible position in each burst frames. We must find the for every burst frame we must find the frame header, and we must attempt each position. So the calculation is very complex. So we are introduced the self-correlation, and we send two group data. They are same. Then we also use the conjugate product to find the peak. It's also free of polarization rotation. So the polarization don't affect the final results. We can say if we use the self-correlations, the result is very flat. And if we use local correlation, the peak is very sharp. So we can find the sketchy position and then find the accurate position by local correlation. Then it's our real-time platform is based on the hardware our 10 giga coherent transceiver product, which I am at the application scene to extend the reach and merge metro and access networks. When we start the 50 ppm clock frequency offset. So we just use the DSA to control the VCO and fix it to maximum and minimal voltage. can watch this result with the Altera debug tools. So you can see the sample phase changed, and they decreased then and jumped to 0.5 and then decreased. It's used the Altera the FPGA debug tools to watch it. We can see this. And the receiving power is adjusted by the VOA in front of EDFA and monitored by the power meters. The BR in different receiving power are recorded as a compilations. We test the BR in continuous mode with recovered clocks. We can see from this graph with 3-stage equalizers, we centralized clock mode has close performance to continuous mode working with the recovered clock. The receiving power sensitivity reached the negative 46 dB. The other important problem is the response speed of DSP to the burst from the same CNU, because we use because when we initialize the second stage, we use the pre-calculated coefficient in the last frames. So the problem is whether it differed. So the key problem is the response of second stage, because the first stage and the third stage is the feed-forward architecture. So their speed is very fast, but the second stage is still adaptive filters. So we must answer the two problems: whether the channel will change and divided from the loaded coefficient by formal adaptive calculation, and the converged speed of the adaptive algorithms. To answer these questions, we define a super-frame group which has 256 frames. The coefficient is only initialized by the first frame. Then the following, the subsequent frame will inherit the revised value and keep updating. So if we will see this graph from the frame 1 to 20, from 200, the BR, the performance is very near. So we can conclude that the result, the loaded coefficient are good enough, and the subsequent adaptive updating improve very little. This result implies for 10 GHz coherent-based transceiver, the second stage equalizer can use the static coefficient with the slowing varying intersample interference effect. So this is the conclusion. We employed a real-time 3-stage equalizer with FPGA for burst mode digital coherent QPSK receivers. With the multifunction parameter headers, each burst frame can be centralized individually with feasible FPGA resource with the 3-stage equalizer. A centralized clock mode has close performance to continuous mode receivings. And the second stage equalizer can use static coefficient for slowing varying intersample interference effect. Thanks for your attention.
Thank you. And now question time. Any questions? Any question from online?